welcome to today's webinar. This is Big Data Architectural Patterns and Best Practices on AWS. Our presenter today is Siva Raghupathy, Principal Solutions Architect at AWS. As the lead for the Americas Big Data Solutions Architecture team at AWS, Siva guides developers and architects to build successful big data applications on AWS. Previously, as a Principal Technical Program Manager for AWS Database Service, he gathered emerging NoSQL requirements and wrote the first version of DynamoDB product specification. This is a very popular webinar, and today's is no exception. It's actually a sold-out webinar. So to help you get the most out of it, we have a panel of AWS Big Data experts online, including Manjit Chajel, Specialist Solutions Architect, Keith Stewart, EMR Solutions Architect, and Babu Elumalai, Solutions Architect. Manjit, Keith, and Babu will engage with you and answer your questions throughout the presentation. So feel free to submit your questions anytime. We'll also try to allocate some time at the end to address additional questions. And with that, on to the fun stuff. So let me turn this over to Siva.
First of all, I want to thank you for being here at this webinar and taking 1 hour of your busy schedule today. I'm delighted to be here. Let's get started. So in terms of the agenda, first of all, I wanted to thank you for coming to this talk. And since you've taken 1 hour of your busy schedule, I hope you'll find this helpful. And I'm going to share some of the best practices and patterns that have worked well for all of our customers here. In terms of the agenda, I'm going to go through some of the big data challenges that our customers are facing and how to simplify big data processing using some principles that have been tried and tested by all these customers. And in the process, we'll break the big data processing into multiple stages: ingest, store, analyze, and visualize or consume. And then in each stage, I'll walk through how to actually pick the right tool for the job. And in addition to how, I'll also cover why it's important, why that tool makes sense. And then towards the end, I'll walk through some of the reference architecture and design patterns. And the volume, velocity, and variety of the big data is ever increasing. What that means to me on a daily basis is customers are demanding to build applications in terms of volume, 100 to 150 terabytes a day flowing into a customer site is becoming normal these days. In terms of velocity, gone are the days of tens of thousands of requests per second being high velocity. Now, high velocity is turning out to be about 1 million requests per second for customers building, for example, online digital advertisement, platforms. In terms of the variety of data, in addition to transactional data, able to build these systems. Customers are able to build these systems in a span of a few weeks or days, often with 1 or 2 developers. And I think the team is having some issues here. Can you guys chime in if the audio is good?
Okay.
Thank you. Are able to build the systems in a reasonably short time. I think they're using some of the tried and tested. I'll walk through some of the tried and tested patterns and how that's possible to build these complex systems really fast. And the other one is, in terms of the evolution, workloads are moving from batch, and prediction is being tied into these workloads as well. For example, instead of a telephone provider sending you a monthly bill, customers today expect an alert if their consumption of their minutes or whatever goes beyond a certain threshold. In addition to that, forecasting what may happen next is pretty important. In other words, if a transaction is coming in, predicting whether this is going to be a high-value transaction or potential fraud transaction is going to be critical in terms of providing the appropriate customer service. So most customers are striving to build predictions into it. How do you build predictive pipelines, prediction into your big data pipeline is another piece that I will touch on as I lay out the architecture patterns. So in terms of the good news here is there's a plethora of tools. On the left side, the Apache open source ecosystem is pumping out an array of technologies, or a zoo of technologies, starting with the classic elephant, Hadoop, to Hive, Pig, Now, if you go to any big data conference, Spark is the answer, no matter what the question is. And similarly for search, Elasticsearch is the answer, no matter what the question is. Now, even though Spark is the answer, there's a little squirrel at the bottom left. I don't know if you know what that is. For people who don't know what that is, it's called Apache Flink. It's challenging that it might be challenging the dominance of Spark. Well, we'll find out. On the right side, we have AWS services, managed services that are very popular for big data, for example, S3 or Elastic MapReduce. Every year, we tend to ship a bunch of new services to make customers' life easier. And the question that comes to a developer's mind or an architect's mind is, how do I build my system, to be able to replace or add in more components as new components come in? Now, your architecture should factor in this. And then the architecture patterns that I'll lay out will allow you to replace some of these components as newer technologies or better technologies come into play. And often the challenge for many developers and architects is, they're a reference architecture. And so I want to lay out the 5 architectural principles that have stood the test of time for me and has helped many customers build very successful systems. The first one is when you build a big data system, you should be building a decoupled system. If you're building a pipeline, which is often the case in case of big data, if there's multiple stages involved, decoupling the producers and consumers through a storage subsystem allows both the producer and the consumer to go at their same speed, at any speed that they want, and it ends up to be a much more robust and a scalable system. Number 2, using the right tool for the job is paramount when you're building high throughput, high processing systems. Because when we build services, for example, when we build services at AWS, we build them to do their function extremely well. And how do you pick the right tool for the job? I'll demonstrate some of this. We'll be using things like access patterns, the data structure, the hotness of the data, etc., to pick the right tool for the job. Third, the Lambda architecture is a very tried and tested pattern in big data. The Lambda architecture is becoming slightly old, but the fundamental principles hold. In other words, when you're building a big data pipeline, keeping an unaltered or immutable log of data that comes in is going to be fairly important, because in many cases you don't know what you'll be looking for, and therefore having the original data in the format that it came in is going to be paramount. And in many cases, rather than building just real-time systems or batch systems, it is more economical to build, systems that would composite both batch and real-time systems and serve a view to the end customer or end application that composites both. I will go through a reference architecture using on AWS as to how to build a system based on Lambda architecture. Leveraging managed services is going to be key. That's what is going to enable you to build systems much faster. There's no point in installing a NoSQL database and then managing the database, for example, updating software, etc. If you can run a managed service that essentially would do the same function at the same cost or lesser cost if you take away the management overhead, for example. Last but not the least, big data should not be equal to big cost. If big data equals big cost, chances are something is wrong in how you're building it. These 5 principles has held the test of time and has been very helpful in guiding me build successful system on behalf of customers. Now, let's use some of these principles to simplify big data processing. So the more pipelines I build, more big data processing sounds like this. Data comes in on one side, and the answers go out on another side. And there's multiple stages in between. Often it is ingest, store, process, consume, or visualize. And the store and process repeats itself multiple times to shape the data in a format that the end consuming application can consume at any rate or any characteristic that it demands. Often this is, what drives what goes in between is what I call time to answer or latency, throughput, which is a function of the request per second and the size of the payload, and cost. So these 3 factors apply. at each stage. So now let's get into the ingest or the collect phase. In the case of ingest or the collect, you may have, in the collection stage, you will have potentially applications or logging frameworks, or more recently, IoT gateways, etc., Internet of Things gateways that may be sending data. Typically, when I look into these applications, there are 3 or 4 types of data here. One, transactional data, file data. So file data and streaming data, those are the predominant data types. When you're dealing with transactional data, when you're dealing with transactional data, it feels like you're multiple times really, really fast. It feels like talking to a database or actually dealing with a cache. If you're dealing with file data, typically what happens is the application servers, let's say if you're processing clickstream logs, one of the ways of processing is the various application servers load the data package this as a file, and then load the data into S3. In the case of streaming data, typically what happens is the data gets written, instead of writing the entire file at a time, each record is being sent as the data is born. And from a storage perspective, now let's walk down into the details of what is in each, what is the best technology to use for streaming storage. Some of the options there are, I've classified this into managed services and unmanaged. In the case of managed services, we have Amazon Kinesis, DynamoDB Streams, Amazon SQS and SNS, even though they're not necessarily, streaming services, streaming storage services. We'll compare and contrast this. I want to compare and contrast this between potentially, the other systems there a little bit later. We'll also look at the unmanaged. On the unmanaged side, for example, Apache Kafka is super popular. Now, why does one use streaming storage? Streaming storage provides the following capabilities. It allows you to decouple producers and consumers. It provides a persistent buffer, so where the producers don't have to hold the piece of data. They can write the data onto the storage subsystem and move on. And it's able to collect multiple streams of data. Probably the most important thing here is the streaming storage subsystem preserve client ordering. By that, what I mean is, in this case, I've shown, for example, a red producer, green producer, blue producer, etc. If the red producer is writing packets 1, 2, 3, 4 in that sequence, as long as it can designate itself with a key, when it does a put into like a Kinesis or Kafka, if it deems the key as read, what Kinesis or Kafka would allow will ensure that the sequence is preserved. In other words, a consuming application can expect the data to come in the same sequence as the producer is producing the data. And so this allows for the consumer to do things like, for example, if you're actually putting clickstream data into Kinesis or Kafka, the consumer can predict where the customer abandoned the cart, because the sequence of data coming in is in the same sequence that the customer actions were happening. And then also it can do things like min, max, if it's measurement of some temperature or pressure, etc. So that's called, that's collectively called, preserving client ordering. In some forms it's also called a streaming MapReduce, but that's really what happens in a MapReduce function. So that happens for free as long as you can designate, you can use the key field during a put in any of the stream storage mechanisms here. And then parallel consumption is also very key. What happens is, often CEOs or CTOs want their distinct teams to consume the same data feed and do processing and produce systems and move forward at their same pace. So rather than one team depending on another team for functionality, both teams can simultaneously work on the data coming in and then run filters and process the data. This streaming storage subsystem allows you to do that. And so what about queues and PubSub? Now, Queues and PubSub have the three common, they also can be used for decoupling producers and consumers, for persistent buffers, and for collecting multiple streams. But what they don't have is the ability to preserve, no client ordering, no parallel consumption, or streaming MapReduce. Those functionalities are not there. The one exception to that is you can pretty much have SNS route messages to multiple queues. That's an exception, but in general, those functionalities are not there. So if you're looking for those, then predominantly using the other storage subsystems are the best answer. So what I've done here is actually gone in a little more deeper. What I've listed on the left side along the rows is the various attributes, whether it's managed, order preserving, delivery, lifetime, etc. And I've compared and contrasted all of these technologies. For example, in this list, Kafka is not a managed service, whereas Amazon Kinesis is a managed service. For example, in the case of order preserving functionality, SQS and SNS doesn't preserve ordering, whereas the other ones preserve ordering. Delivery, this is a very important attribute. For example, if you're building a building or a metering system, you don't want to double bill your customer. So if you depend on the stream storage subsystem to do deduping for you, you should look for one with exactly one semantic, or you should build that semantic into your application to be, for example, using a database such as NoSQL to do, DynamoDB, I would say, to do deduping, so the customer sees, not two records for the same, not double billed, for essentially. In terms of the lifetimes, the data that you put in Kinesis stays there for 7 days. It's 24 hours in a DynamoDB stream, but the data is persisted forever in the DynamoDB table there. Again, it's 14 days for SQS or SNS, etc. I'm not going to go into every detail here, but I wanted to lay out some of the characteristics that you can actually, we'll provide these slides for you, so you can actually use this for comparing and contrasting various services as you're making a decision. Last but not the least, using Kinesis is probably the lowest cost option there, and then especially if you consider you don't have to, Kafka is also low cost, but admin cost adds up there. So those are some of the factors that I want you to consider. Now, moving to the next subsystem for file storage, S3 is the ideal place for putting, storing your big data files, if you will, because it natively supports a large number of formats, big data frameworks such as Spark, Hive, Presto, etc. Then it decouples storage from processing, that there's no need to run a compute cluster for storage. You can simply, write data to S3 at any rate that you want. You can also run, since the data is not volatile, it's not sitting on a cluster of machines, you can basically turn off your cluster. You can probably use pod instances, or turn off your cluster if you don't need to be processing the data, and then still collect the data from the downstream applications writing to S3. And again, there's many advantages there. S3 also has very high durability. It also has tiered storage options. It's very secure, supports both encryption and flight as in rest, and it's fairly low cost. Anywhere from 3 cents per gigabyte per month to below. And what about HDFS? HDFS typically is being used less and less, I would say, and mostly it's being used as sort of an intermediate storage mechanism between two stages of Hadoop processing, if you will, or big data processing, if you will, rather than writing it back to S3. But even that, is writing to S3 is pretty performant, I would say. And then, so my general recommendation would be, yes, if you're all use HDFS, use this as just an intermediate mechanism for parking your hot data or access for hot data sets, and then eventually park the data in S3. S3 also has multiple storage classes, such as S3 standard and standard infrequent access. So as your data gets less frequently accessed, I would set a policy to move the data set from standard to infrequent access to Glacier, for example, for cold storage. So moving on into the storage tier, this is not how to build your storage tier. In other words, relational databases have been around for 30 plus years. They do their function extremely well, but it is very hard to scale a specific dimension. For example, if you need a big screwdriver, you need to buy a big Swiss Army knife to get the size of the screwdriver that you want. What you want to be doing, for example, is rather
picking a tool that would do the job very well. For example, if you're using a NoSQL, if you need 1 million requests per second of reads and 100 requests per second or 1,000 requests per second of write, you can simply ask for a provision throughput of 1 million reads per second and 100 writes per second, and that's not possible by doing it in a relational database. So if this is not, if this is an anti-pattern, so what is the pattern? The pattern is really thinking of your database and search tier as comprising of a cache, NoSQL, SQL, and search. Often when I say this, the next question that comes to mind is, well, how do you really build a system? How do you keep this in sync? This becomes a little bit of a challenge, but the data can be eventually consistent. Here is systematic where, in this case, what I'm showing here is, data set being written to DynamoDB, and there's an update stream for this table, and you can either use Kinesis consumer library or AWS Lambda to process the data and upload the data or update the data onto your search, Elasticsearch or Cloud Search, or also keep some caches warm. So this way, even though there may be about a 50 millisecond to 100 millisecond delay there, that suffices for many classes of applications. Is becoming very popular. So that's one way of keeping these various storage mechanisms in sync. What storage should I use? It depends upon the data structure, access patterns, and data characteristics such as hot, cold, or warm, and the right cost. We'll go through some examples there. So in terms of the data access patterns, if you have a put or a get access pattern, using caches or NoSQL is the right answer. If you have a simple relationship such as one-to-many or many-to-many relationship, using NoSQL comes in, works fairly well. And if you have, on the other hand, if you have, cross-table joins and transactions and rich SQL, obviously SQL or relational databases are the ideal place for doing this. And if you're dealing with faceting and search, clearly search is the right mechanism or the right storage subsystem to use. And in terms of the database structure, if you have a fixed schema, SQL or NoSQL would work. Schema-free, NoSQL or search would work. If you have a key value, caches or NoSQL would be the ideal option. So the other factor that often I think about when I help customers build big data systems or storage subsystems is what is the temperature of the data that I'm dealing with? Typically hot data comprises of small pieces of data moving extremely fast. Maybe tens and thousands of requests per second. If the request per gigabyte is very high or the frequency access is very high. As you move towards the colder data set, the frequency of access becomes low, but the data set sizes or the file sizes are typically bigger. The cost is higher per gigabyte on the hot data for the hot data sets because typically it's in RAM. And then towards the colder side, it's in spinning disks these days. So the cost tends to be lower. So what I've done here is actually, on the left side, left top, you have low to high data structure. For example, stuff you put in HDFS is low, or S3 is low, versus stuff you put in SQL or search is higher. And then along below, I've had various request rates, cost per gigabyte, latency, and data volume. And so this is sort of the mental map that I have, which goes, these are the various types of tools, to use based on the spectrum of hot to cold. And in the next slide, what I've done is I've chosen specific services there to overlay the hot to cold, data paradigm. For example, Amazon Elasticsearch, you can use a couple of engines there, Redis or Memcache. For example, is typically used for doing, storing hot data sets, very low latency, anywhere, 1 millisecond or less if it's another AZ especially. And the cost in the data volumes typically in the order of gigabytes is what people typically keep. The item sizes are in the order of bytes to kilobytes, and the request rate tends to be high to very high, and the storage cost per gigabyte tends to be slightly higher. As you move towards the right, in the case of DynamoDB, the average latency is about 3 milliseconds. Item sizes are about 400K, etc. I'm not going to go through this entire slide, every item here, but I think this is a good reference. Many customers found this extremely helpful as they're building or they're choosing data stores. Sometimes when you are picking a data store, maybe 2 data stores may do the job, for example. I'm going to illustrate that with an example next. This is where being cost conscious comes in very handy. For example, here is a question that I got from an Amazon developer. The person is trying to choose between Amazon S3, Amazon DynamoDB. The story goes like this: I'm curious, scoping out a project that will greatly increase my team's use of S3. Hoping you could answer some questions. The current iteration of the design calls for many files, perhaps 1 billion during peak. The total size would be in the order of 1.5 terabytes. When I ask more specific questions, I get data like this. The person is trying to do 300 writes per second. The object size is 2K. The total items stored per month, total size of the payload stored per month is 1.5 terabytes. And then, it boils down to storing, 777 million plus million objects in the, in the storage subsystem. Now, what is the tool that you should use for it? If this is live audience, I would ask you to lift your hand on whether S3 or DynamoDB. It turns out people, some people say it's S3, some people say DynamoDB. So what I often do, I don't know how many of you have looked at the simple calculator. It comes in very handy in situations like this, or more. For example, if you plug those numbers into simple calculator, it turns out in this case, DynamoDB is going to cost $644 versus S3, which is going to cost $3,932. It is contrary for some people who picked S3. They're totally surprised. But it turns out, storage cost in S3 is fairly cheap, but S3 is designed for slightly bigger objects, maybe not that many tons of requests per second as you would write to a database, for example. Therefore, the put and the list cost tends to be slightly, higher. That's what is making, the DynamoDB very favorable in this case. But it's just this is just one dimension. And so, being cost conscious often helps you pick the right tool. When I showed this chart to the S3 product manager, the person was not very happy, but then eventually agreed with me. But still, I wanted to put a compensating scenario to highlight S3's how cool S3 is. So I added another scenario 2, where I've changed the object size from 2K to 32K. So it turns out in that case, S3 is the winner. S3 is going to cost $4,588 versus Dynamo is going to cost $10,000. So I think it's just a simple example, but I think it's a real example. Plus, it gives you a sense of how you should use cost as one of the guiding principles as you build your big data pipeline, if you will. In terms of the process to analyze, there is essentially 4 different types of analytics. When I talk analytics, people talk about either interactive analytics or batch analytics or real-time analytics or machine learning. So in the terms of interactive analytics, you're dealing with somebody is sitting in front of a dashboard, slicing and dicing data. They expect the answer to come back in seconds, and so on. And in the case of batch analytics, people are taking large volumes of data. You can run you run a hive or a big job that comes back in minutes or hours to generate the answers. Classic examples are daily, weekly, or monthly reports. In the case of real-time analytics, again, it comprises of sort of near real-time, where you're doing like 1-minute metric or the number of orders received per minute. For example, for Amazon.com, we constantly track our number of orders received per minute. So if there's any dip, we look at all our systems very deeply to figure out what may be going on there. So that's a very important metric for our business. In the case of real time, for example, alerts is a classic example. When there is a strange event that is happening, you want to basically, if the pressure or the temperature gauge is going out of whack, you want to trigger an alert so somebody can take care of this equipment. Or if it could be a billing or a fraudulent alert as well, or classic examples of real-time analytics. Predictions are where machine learning gives computers the ability to learn without being explicitly programmed. There are 2 general classes of machine learning algorithms. One is supervised machine learning. The other one is unsupervised machine learning. In the case of supervised machine learning, you teach the program using some sample data sets, and then you ask a question such as, is this transaction fraud, yes or no? Or, how much this house is going to, how much this house will sell for. It has 2 bedrooms. It is potentially in this zip code. What should I expect? Or if this new customer is coming in based on the various characteristics of the customer, potentially age, zip code, etc., that they live in, what would be the lifetime worth of this customer? It'll be important to, if you predict this about a new entity or a customer coming in, then you can provide a very customized experience. That's probably the best. It's going to be very crucial to do these. Also, in the case of segmentation or clustering, we have, for example, a large number of shoes or clothing in Amazon.com. We use clustering algorithm to basically classify them into what type of products these are, so we can do faceting with these mechanisms. So in terms of analysis tools and frameworks, these are the popular ones. For machine learning, most people started with Mahout, and a lot of people are using Spark, ML, and Amazon Machine Learning is super popular as well because it simplifies many, many things for developers there. And then for interactive analytics, typically Redshift, Presto, Impala, or Spark are classic solutions there. For batch processing, clearly MapReduce, Hive, and Peg are still super popular. And for stream processing, Spark Streaming is very popular, versus also AWS Lambda is becoming super popular these days. And then Kinesis Client Library also is popular there. In terms of the various Amazon Elastic MapReduce, you're able to run all of these applications such as Presto, Impala, Spark, either natively or as a bootstrap action. And obviously, Amazon Redshift is a managed service, is a fully managed service. Amazon Elastic, Amazon Machine Learning is also a fully managed service. If you're running Spark, you can run Spark Streaming on top of Elastic MapReduce as well. Similarly, Kinesis and Storm can be run on EC2, and AWS Lambda is a fully managed service. So what stream processing technology should I use? What I've tried to do is to compare and contrast these technologies. I'm not going to go through every single square there, but I'm going to highlight a couple of things. For example, people often forget when they're dealing with a choice, the fault tolerancy of the subsystem that they're building. For example, Spark Streaming, still is a single easy solution, whereas if you use KCL, Kinesis Client Library, and AWS Lambda, if your data is in Kinesis, these are inherently multi-AZ. So even if one data center goes down, you don't have to, automatically your workload gets rebalanced, through the auto-scaling group that we have, or AWS Lambda automatically handles this for you. Therefore, if you have very highly available system, then you should think about maybe bringing up, if you're running Spark Streaming, to bring up another Spark cluster to be able to process the data. So that's just one example. But in general, Spark Streaming, Storm, Kinesis Client Library, and Lambda can be used for very low latency processing, whereas Hive and Peg, the latency processing is higher. Similarly, Amazon Redshift, is very ideal if you're dealing with a classic MPP, massive parallel processing data warehouse. Now, Presto and Impala are open source systems that essentially do the same. And then, Presto, for example, Netflix uses Presto for their billing system. They're super happy with that. Impala recently added support for S3, which is super interesting there as well. So I think I've tried to classify overall, if you're looking for low latency query processing, I would probably start with Amazon Redshift and explore Impala or Presto, Impala or Spark if you're keen on using an open source system. Similarly, Hive has been tried and tested as a batch processing engine of choice. So Hive with Test allows you, speeds up Hive processing a lot. Test is a new engine as well. So and then moving on to ETL, AWS Data Pipeline is a service that enables you to do ETL, and that actually under the covers can run an EMR cluster, process the data and shut down the cluster. In addition to that, customers are using third-party applications such as, these are partner applications that we closely work with these partners. Informatica, Attenuity, Matillion, this is just a subset of the partners that we have. These systems work very well, for example, and they've been around for a long time. So I think, in terms of ETL, looking at partner solutions in addition to data pipeline, will allow you to pick the right solution there. In terms of consume and visualize, there's two personas here. One are you're either dealing with data scientists and developers, or you're dealing with business users. Business users typically want to use something like Amazon QuickSight, which is fairly recent, that we shipped for doing visualization of your data and analysis of your data. Tableau, Looker, TIBCO, MicroStrategy are all fairly popular. Also, you have other libraries such as D3 or Flock or Kibana is also very popular for actually drawing beautiful graphs, if you will. Notebooks, especially with the data science audience, notebooks are getting very popular. Running Apache Zeppelin or IPython notebook on top of Elastic MapReduce is also getting super popular. In fact, AWS, if you look for AWS Big Data blog and search for either Zeppelin or IPython, you would actually have articles that walk you through how to set up these systems. Most scientists are super happy, and they are actually playing with these as well. RStudio is fairly popular. The other piece is also, on the consume side is also apps and APIs. In addition to human consumers, you also have other consumers consuming this. I will touch on this during, in a few slides later during the Lambda architecture slide as to how do you build a downstream application on top of a consuming layer as well. So putting it all together, here's the reference architecture, and I leave this for your reference. I think this is probably the single page, if you want to actually that actually categorizes all the various options that we discussed. And I'm not going to go into specific details here, but we covered most of this so far. So now let's go into the design patterns here for a few minutes there. Now, when you're building a big data pipeline, thinking of this as multiple stages, store, process, makes a lot of sense, because then the various processing subsystems can run at their own speed. They're nicely decoupled, and then so the entire pipeline, the workflow flows through the pipeline fairly efficiently. And then this also allows you to build subsystems such as you can have multiple processing layers process the data from the same storage subsystem. In this case, you have Amazon Kinesis S3 connector as well as AWS Lambda processing data in Kinesis, and then actually one stores it in DynamoDB, other pre-processes that and puts that in S3, for example. Setting the pipeline in such a way also allows you to have multiple processing frameworks. In this case, Hive can manipulate data or join data between what's in DynamoDB through the Hive handler, as well as through S3, and then you can actually do a select query that joins the data from both of these data sources. And now what I've done in this slide is a very busy slide. Let's move from top to bottom. On the top I have the data hot to cold. Kinesis and Kafka being hot data stores, and then DynamoDB being a hot data store. As you move towards the right, towards S3, it becomes a warm data store. On the vertical axis, which is the y-axis, the processing latency goes from low to high. And if, for example, for real-time processing, you could potentially use Spark Streaming or AWS Lambda or Storm to process data in Kinesis so basically you're using a hot data store as well as a low latency processing mechanism to get the answers very fast. As you move towards the right side, now for interactive analytics, you potentially put the data in DynamoDB or HDFS or S3, and then either, if you put it in DynamoDB, you can copy it to Redshift, or if you put it in S3, you can copy it to Redshift and run an interactive query. And similarly, you can also use Spark, Impala, and Presto to run queries on top of both data in HDFS as well as S3 for interactive analytics. For batch, similarly, you can use Hive for running batch queries. So now let's look at specific scenarios. Real-time analytics. This is how I would build. This is sort of a reference architecture for building a real-time analytics system on AWS. Your producer typically sends the data into Amazon Kinesis or Kafka or DynamoDB Stream. For the most case, I would pick Kinesis unless you have a reason not to, and for most scenarios. And then, once the data goes there, you can either use AWS Lambda, which is a completely managed subsystem. All you do is write functions to process the data, or you can use KCL, Kinesis Client Library, if you need, if your computations can't run within 5 minutes, for example. You can use KCL to process the data. And then if you need an alert, if you need a system that needs to do alerting, you can use Amazon SNS to do the alerting. Or if you're rendering various KPIs, you can use a nice decoupling mechanism such as Amazon DynamoDB or RDS to put the data in a shape that you want, so the downstream visualization layer can actually render the data in terms of a graph. And in addition to this, you can also consult Amazon Machine Learning Service for doing real-time predictions. If a specific transaction is coming in, you can basically ask the Amazon Machine Learning to say, is it fraud or not, yes or no, and based on that, you can actually send an alert or not. So in terms of interactive analytics, here's the classic architecture. Your producer puts the data in S3, and then data gets either copied to Redshift for doing interactive analytics, or you're using Presto, Impala, or Spark to do interactive analytics, and then you consume the data. You can also do either real-time predictions. You can, via Amazon Machine Learning, for example, you could write a function and then have the function look up machine learning service for either doing classification, for example, or finding an yes or no answer, and interface that interaction as well. And for batch analytics, similarly, you can have either Hive or Pig or Spark SQL process the data in S3 and then render a report or a weekly, monthly report, for example. So the same idea of decoupling the system allows you to build a very, very scalable pipeline, if you will. Again, Lambda Architecture. So here I have data going into Amazon Kinesis, and then I'm building a batch layer where I'm writing an Amazon Kinesis S3 connector to put the data in S3, and then they can be copied over from S3 into Redshift or EMR using one of those tags, Presto, Spark, Hive, or Pig, to surface the answer. Now, if this is the only thing that you're doing, then potentially you could use Kinesis Firehose for that. You don't have to have the Amazon Kinesis S3 connector. Instead, if you wrote the Kinesis Firehose, it automatically pushes the data to S3 or Redshift if your final destination is Redshift. And then speed layer, if you're building, let's say, windowing functions and others, you could have them built using Spark Streaming or Storm or AWS Lambda, if you will, or KCL. And then typically what happens is, here's where I was pointing to. If the downstream applications are dependent on this, in some cases the downstream applications can do, may not necessarily be a human consumer. It could be a subsystem that's doing, tens or thousands or even millions of requests per second. So your batch layer and the speed layer should put that into some form of a storage subsystem. It could be either Amazon DynamoDB or RDS or Elasticsearch to be able to surface the answers in, depending upon what type of, if it's a search problem, then typically data goes to search. The same principles that we discussed apply. So it's pretty critical to actually have a serving layer that serves the data in a form or shape that's required by the downstream application. So obviously you can put in Amazon Machine Learning, the black box in the middle, to supplement the computation to add more intelligence to the answers that are being surfaced. And with that, I want to summarize. So building decoupled, when you're building a big data pipeline, building a decoupled system is important. The way it looks like is data goes into storage and then it's processed, and then that store process repeats itself until the data is shaped in a form that caters to the downstream system. Using the right tool for the job is paramount, and we walk through how to use potentially latency, throughput, and access patterns to pick the right tool. We walk through AWS Lambda architecture pattern where we went through, in this case, the Lambda architecture, I showed you how to write a immutable log into S3, and then how to use batch and the speed layer to build a serving layer. And then leveraging managed services wherever it's possible is going to be key, because you don't have to deal with administering the system, updating the software, etc. Last but not the least, being cost conscious is critical, and that's going to often lead to the right solution. Thank you for your time. And really appreciate you coming to this session.